Hello everyone, welcome to lecture number 4 of week 3 on the course Power Network Analysis, in which we continue our discussion on the module Synchronous Generators. In today's discussion, we will understand in detail how the real and reactive power output of a synchronous generator, to be specific, can be controlled, regulated, monitored, so that the corresponding control power can be regulated accordingly through manual intervention, or there are also automatic control loops which do that. But then these control loops, they also have to manually trigger or perturb some entity in the setup of synchronous generators so that their corresponding real and reactive powers are regulated as and when required. So we'll understand those points or items or quantities which are regulated and how their consequence appears on real and reactive power exchange. That's what we will discuss today. In the previous lecture, we discussed at length about what capability curves are, how do we get the points on the PQ domain, complex plane domain, marking all those safe operating points for a synchronous machine to be general, regarding maximum armature current limit, maximum field current limit, and maximum steady state real power limit. So we understood all that, and those understanding also involved two critical equations: the real and reactive power expressions for a cylindrical pole synchronous generator with negligible armature winding resistance. So we'll also use those expressions in this discussion to understand how the control can happen from the power perspective. So that's where these expressions of this slide comes into effect. We have a cylindrical pole rotor, a cylindrical pole synchronous generator with negligible armature winding resistance, and for that we have this as our real power expression and this as our reactive power expression. And we had also seen this expressions earlier, where we understood that if the synchronous machine has to behave as a generator, wherein a generator converts input mechanical power to output electrical power. So for a generating mode, the real power expression P, if it has to be positive, the only possibility for it being positive is that in the P expression, VT, EF, the terminal voltage, induced EMF, synchronous reactance, they are phasors, they are scalars, basically magnitudes of phasors, so they have to be positive. There is no way that they can become negative. The only possibility for P to become positive is only when sine delta is positive. So for sine delta to be positive, delta has to be positive, and that's how for real power transfer in generating mode, delta is inherently positive, means the induced EMF always leads the terminal voltage in a synchronous generator. In a motoring mode, where motor converts the input electrical power to output mechanical power, so in a way real power is being absorbed, the P value has to be negative, and for P to be negative in motoring mode, sine delta has to be negative, which is only possible when delta is negative, and that is why in motoring mode induced EMF always lacks the corresponding terminal voltage. Similarly, for reactive power transfer, irrespective of motoring or generating mode, if the machine has to deliver reactive power, that means the term which is sitting here, which is the part EF cos delta minus VT, when it becomes positive, which is what is shown over here, then only the reactive power will be delivered, and for the machine to absorb reactive power, EF cos delta has to be less than terminal voltage. Now, one thing I'll specify or pinpoint before we go deep into our discussion, that when the machine or synchronous machine, to be specific, is delivering reactive power, that means there has to be some device which is absorbing this reactive power. So basically what I'm trying to say is, for machine delivering reactive power, the associated load which is connected to this synchronous generator, it is inherently an inductive load, because inductive loads tend to absorb reactive power. So in a way here reactive power is being absorbed, And this absorption of reactive power is happening because the generator is able to deliver this amount of reactive power. Now, when a load is absorbing reactive power, when it is an inductive load, we tend to define our power factors specifically from perspective of loads and not generators, because load drive the entire system, and hence power factor notion also comes from the notion of how loads are operating, which means that if there is a synchronous generator which is delivering reactive power to an inductive load, we would say or infer that the synchronous generator is feeding a inductive load which is inherently of lagging power factor. So, under overexcited mode, which we will see in a moment, the intuitive load which is connected to this machine has a lagging power factor. Now, when the power factor is lagging from the perspective of load, that means the corresponding armature current which is being fed from the generator is also lagging its own terminal voltage, because power factors, as I said, are being defined from perspective of loads, not from perspective of how the sources are operating. If there would have been no loads, there would have been no need of electrical power network, there would have been no need of electrical sources. So that's how the notion should be there, that for reactive power delivered, the machine is behaving as a capacitor. Its own power factor becomes leading, but then to compensate for this leading power factor or reactive power deliverance, the load is of inductive nature and its power factor is lagging. Similarly, for underexcited mode, the load has to be a capacitive load because machine is absorbing reactive power. So, load is behaving as a capacitor which usually operates under leading power factor mode. So, when we say machine is connected to a particular load having some power factor, the power factor is inherently the load power factor, not the machine power factor. So, having discussed these expressions, let's now see how the control aspect can come in. We have talked about isolated synchronous generators at length, but if we talk about the entire power network, we have seen that generators need not be present at same locations where the loads are, and that's where there is a need of transmission network. And since there is a network which is sort of acting as a passage between power generated to power delivered, we often don't have isolated synchronous generators which operate in isolation. So that's the reason why this statement comes, that an alternator rarely delivers power to individual loads. It transfers its powers through a power network which consists of several such buses. And when this alternator is being connected to the corresponding power network which has few far off distributed loads, there's a process which is followed, which we will see in the next immediate slide. And often, for the sake of analysis, we consider the bus where the alternator is connected in the power network. We call that bus to be an infinite bus. The term infinite here refers to the fact that it can absorb or deliver any amount of real or reactive power. Ideally speaking, yes, it is good to have this notion. Practically, we don't have infinite buses in power networks because no such bus or no such device or element or load will have this capacity of absorbing or generating any amount of real or reactive power. It is only from the mathematical analysis perspective, for the sake of simplicity, if I would say, that to mathematically analyze our systems or generators, we consider the bus to which the generator is connected to be called as the infinite bus. And to some extent it might make sense, because when we say a generator is being connected to a power network, the power network is a huge geographically spanning network operating at different voltages, having several transmission lines, distribution lines, transformers, loads of different types, etc., etc. So, if we compare the capacity of power which is being handled in this power network, which could be in the order of few gigawatts. Remember, India's installed generation capacity is close to around 450-60 gigawatts. If we compare one generator whose capacity is, let's say, of few megawatts, compare this generator of few megawatts to a network which is handling power of few gigawatts, there is actually no comparison. This standalone generator will probably not significantly perturb the voltage and frequency of a network which is handling gigawatts of capacities of power, and that's where the notion of infinite bus to some practical sense makes sense. So that's the reason why Practically, a bus to which a large load or a large generator is connected behaves or tends to behave as an infinite bus, which doesn't have much perturbation in its terminal voltage and frequency, and hence we can call that to be an infinite bus. It also has to do with the inertia which is present in the bus from the effective inertia perspective, which we'll also talk about in detail in the last module of stability analysis, that how system inertia helps in strengthening or weakening a bus from the infinite bus perspective. So the process of how this generator is connected to, a new generator is connected to the power network, is known as synchronization. There are 4 simple steps in ensuring that the machine is synchronized. The first one is ensuring that the terminal voltage of generator and the terminal voltage of bus where it is connected, they should match. The frequency of generator and infinite bus, they should match. The corresponding phase sequence A, B, C or R, Y, B, the same sequences should be connected, and the phase connection, the phase difference should be 0. Now, the reason why these steps are important to ensure before loading the generator to generate some power is, if we have a generator whose terminal voltage magnitude is different from the terminal voltage of the infinite bus, that means we are trying to connect an active device or a generator whose magnitude is more compared to a bus where the voltage magnitude is less. So essentially, these 2 points will have a potential difference, and in between this potential difference, if we have a switch which is supposed to be closed to ensure synchronization, there are safety hazards involved in closing switches when the potential difference across the switch is not 0. So ensuring terminal voltage magnitude is same, phase angle differences are same. Even if magnitudes are same, phase angle differences don't exist. If we start connecting A, B, C of generator to capital ABC on the grid side, let's say this is a generator terminal and this is the infinite bus, if we have ensured terminal voltage magnitude and phase angles to be same, and now incorrectly we connect phase A to phase B to phase C to phase A, we would definitely have line-to-line voltages between these switches. And again, if we close the switch with some non-zero potential difference, there might be safety hazards. So those are the issues or reasons behind ensuring these quantities to be matching. The last term which is to be matched is frequency. Again, the first 3 terms, or to be precise, the terminal voltage magnitude has to do with how much of reactive power dominantly is being generated or absorbed. When we close the switch to ensure synchronization between generator and infinite bus, at this condition, we ideally are ensuring that there is no reactive power exchange happening between generator and the infinite bus. Similarly, if we ensure frequency to be matching for both generator and infinite bus, we are ensuring that at that point of synchronization, ideally no real power is also getting exchanged. And those are again from the perspective of safety for the operational perspective as well as the synchronous generator to which is being synchronized. Practically, there are little differences. In practice, the frequency of incoming alternator or generator is kept little higher, probably somewhere around 0.01%, so that the machine by default, again, any machine ideally speaking can behave as a generator and a motor. But now if we have a specific alternator which is designed to behave as a generator, it at any point of time should not ever absorb real power. That is one reason. The other reason is generators also have power directional relays from the perspective of power system protection, which inhibits this generator to behave ever as a motor. If it starts behaving as a motor, then the corresponding turbine which is driving the generator would become the mechanical load. Machine behaving as a motor will start driving the turbine, which can have its own implications if it is a steam turbine or a hydro turbine too. So from the safety perspective, the synchronous generator should always deliver real power. To ensure delivering real power, the frequency of incoming generator is kept little more, maybe somewhere around 0.01% compared to standard system frequency, so that machine starts generating real power. That is the reason. So essentially, if we recollect capability curves discussion, there also we had emphasized that all our capability curves are from the perspective of fixed terminal voltage and fixed synchronous reactance. In the process of synchronization also, we are ensuring that the terminal voltage of synchronous generator is matching the voltage of the infinite bus or the grid supply. So that's the reason why an alternator, when it is connected to an infinite bus or a grid, will typically always have fixed terminal voltage, and it will also have a fixed synchronous speed or frequency. Frequency and synchronous speed, they go hand in hand. In fact, synchronous speed in RPM is 120 F by P, where P is the number of poles induced in the rotor or the stator windings, or the MMF perspective, and F is the frequency. So, to have or understand the control action behind real power and reactive power, we have two entities which can be controlled at the outset. The first is regulating the rotor or the field current, which is DC current from the rotor excitation perspective. And the next control which can come in is from the perspective of turbine, which is feeding in mechanical torque or mechanical power to the synchronous generator. The variation of rotor field winding primarily governs the reactive power delivered or absorbed by the machine, whereas the mechanical torque control primarily governs the real power which is generated by the corresponding synchronous generator. So, in this particular discussion, we will talk about these controls at length, and then we will try to understand how their implications can come in. So, we will first start with the excitation control or power factor control or reactive power control, in which the rotor field winding is regulated, varied as per the requirement, and by doing so, what happens is the induced EMF, EF or ERMS value changes. In a way, the corresponding torque angle might also change depending on whether the real power is kept fixed or not, and change in the induced EMF in a way significantly regulates whether the stator current is leading or lagging the terminal voltage. What we would do for our sake of discussion is, to make it simple, we will consider the reactive power control for a specific machine. That machine is a cylindrical pole synchronous generator with negligible armature winding resistance, Ra almost being 0, and we also will sort of recollect that when the machine armature current is lagging the terminal voltage, the machine is in a way feeding in an inductive load which is hungry for reactive power. So, the machine is actually delivering reactive power. That notion in mind, we will now try to see how the reactive power control comes into effect. So, we are talking about this particular machine, cylindrical rotor synchronous generator with negligible armature resistance, whose expression for real power is P is equal to EF Vt sin delta by Xs. And in here, the terminal voltage is a fixed quantity because generator is synchronized. The synchronous reactance is also fixed because it's a machine operating in steady state, so these cannot be changed at all. The things which can regulate individually are EF with sin delta and also Ia with cos theta. These quantities in this, basically armature current, impedance angle theta, induced EMF and the torque angle, these four quantities they can change. Now, if we put a constraint that we are doing or trying to understand reactive power control for fixed real power, that means if P phase has to remain constant, then this constancy can only happen only when Ia cos theta, where Ia and theta individually are varying, Ia cos theta and EF sin delta remain constant, because Vt anyway is constant because machine is synchronized and Xs is a fixed quantity. So, in order to understand reactive power control, we will have this constraint where these two are the enforcements or constraints. So, let us see how this enforcement can come in. So, before I dig deep into the next slide, let us also recollect that for a cylindrical pole synchronous generator with negligible armature winding resistance, the corresponding phasor equation which defines its operation with terminal voltage being as a reference is EF at an angle delta is equal to Vt at an angle 0, where Vt is the terminal voltage, per phase terminal voltage acting as a reference for all phasor quantities, plus Ia phasor into Jxs, where J is the complex operator, Xs is the synchronous reactance. Depending on whether the current is leading or lagging, this Ia phasor can lead or lag the corresponding terminal voltage accordingly. Delta is the torque angle of induced EMF with respect to terminal voltage. So, if we have this as our equation, we also know how its phasor diagram would look like. All these quantities are phasors. So, that phasor diagram essentially are the lines which are the yellow line, orange line and the red line. I have intently mark these lines so that we can correlate this orange, yellow and red line as the corresponding voltages which are marked or written in this corresponding equation. So I am initially considering a condition where the armature current is lagging the terminal voltage by an angle theta, and having defined this phase angle, I can also probably get to know what is the torque angle, which is this angle delta, and also the induced EMF. Now in this phasor diagram, if I have to ensure that no matter what quantity is being regulated for reactive power control, IA cos theta and EF sin delta have to remain constant, because machine's real power output is being kept constant. So the locus which indicates IA cos theta and EF sin delta to be constant are the respective blue and purple color lines. Now how do I get that? Now since I have already marked the angle theta, remember the perpendicular distance in front of the angle theta is associated with sin theta. The corresponding base dictates the quantity which is cos theta. Now if theta is known and cosine theta is the base which is defining this cos theta, and it gets multiplied with armature current IA, that means this origin or point, its distance from this blue color line, which is measure of IA cos theta, should remain constant. So that means if I have to draw the locus of IA cos theta, it is a line which is perpendicular to the yellow color line. That's how IA cos theta is getting marked. Similarly, EF sin delta, if delta is this angle, then the perpendicular in front of angle delta is sin delta. EF sin delta is the component here which is multiplied. So basically the origin or the point with respect to EF sin delta should always be constant. So basically the locus of EF sin delta is a line parallel to the yellow color reference, which is the voltage terminal reference. So having understood these locuses, now let's see how a reactive power control happens. Reactive power control happens by variation in the rotor current, which is IF, because IF changes the maximum flux per pole, which in a way changes the induced EMF. Induced EMF is typically mathematically defined as 4.44 N phi F into F, where phi F is this particular maximum flux linkage per rotor pole defined by the armature, the field current IF. So we consider one condition. Compared to field current IF, which I have considered here, I now reduce the field current to IF1. If IF1 is reduced, which means the induced EMF will also reduce. So EF has to reduce, but EF can reduce only on the condition that EF sin delta remains constant. So now if EF has reduced to, let's say, EF1, which is this number here, to maintain EF sin delta, which is a constant number, the corresponding torque angle should increase. So delta 1 is that particular increase with respect to delta, so that EF sin delta can remain constant. And likewise, if EF sin delta is marked, I can also get to know what is the corresponding voltage drop across the synchronous reactance, from where I can indirectly figure out what is my armature current. So what I see is my armature current magnitude has gone down. If armature current magnitude has gone down, IA cos theta should remain constant. That means cos theta should increase. Cos theta can increase only when the impedance angle is reduced. So IA1 and theta1, they adjust accordingly, so that IA cos theta is also constant while ensuring the KVL satisfactory for the synchronous generator. And in this case, what I see, if I compare or revisit my reactive power expression, EF cos delta, which is the component of EF, orange color line, along the yellow color line, this is the entire EF1 cos delta 1 component. And for this excitation current, what we see here is EF cos delta 1 is definitely more than the terminal voltage. So reactive power is positive, which means the machine is delivering reactive power. It is overexcited and hence it is delivering reactive power, and it is delivering reactive power, so this power has to go somewhere, and that's where the load is lagging load. Basically, it is an inductive load. Now, if we keep reducing the field current, let's say we come to a field current IF2, where EF2 cos delta 2 is exactly same as VT, which means the reactive power output is perfectly zero, then in that condition for EF sine delta, so EF2 cos delta equal to 0 means the delta 2 angle has definitely increased from delta 1. And if reactive power is 0, that means VT IA sine theta is also 0. VT cannot be 0. Armature current is a magnitude. So IA is the magnitude of armature current. So that cannot be 0 because real power is still being maintained constant. So theta has to be 0 for Q to be 0. And that's where theta, green line and yellow line, they are parallel. So EF sine delta is constant, delta 2 is more than delta 1, theta is perfectly 0. No reactive power exchange is happening, and basically the machine is operating under unity power factor mode. If we furthermore reduce the excitation current to IF3, EF magnitude would decrease, torque angle would increase so that EF sine delta becomes positive. Now the current would start leading the corresponding terminal voltage, and it would behave as an under-excited operation mode where reactive power is being absorbed, means the load is a capacitive load and hence it's operating at leading power factor. That's all about reactive power control, under-excitation, over-excitation. If we talk about real power control, which is essentially driven by the output of the prime mover of the turbine, it in a way regulates or has significant impact on the torque angle delta, which happens by opening or closing of turbine valves, feeding in more power, more water or more steam. That means the mechanical output of turbine is increasing, so the machine, synchronous generator, tends to get more mechanical input. So that happens electrically through physical observation of change in the torque angle. And this torque angle essentially creates an advancement or a retardament between rotor magnetomotive force and stator magnetomotive force temporarily. So for that moment of perturbation with constant excitation and increase in turbine power momentarily increases the synchronous rotor speed. The speed tends to go beyond synchronous speed and hence torque angle also increases. But eventually in steady state, the increase in delta tends to increase IA cos theta, so the machine tends to deliver more real power. But in steady state, because of armature reaction and thanks to damper windings, the rotor MMF and stator MMF, they again balance out each other. The speed again restores to synchronous speed, and that's the reason why synchronous machines operate at synchronous speed only in the steady state conditions. During disturbances or perturbations, there are deviations of the speed different from synchronous speed in synchronous machines. And the restoring action comes in because of armature reaction and the damper windings, which we discussed at length, which we'll also talk about in length when we talk about stability analysis module as well as the fault analysis module. So in a way, through real power control, the prime mover and the rotor and the rotor MMF, they again re-established, ensuring that the system frequency and generator frequency, they match each other. So just to summarize about power factor control, if we have a generator with rotor current IF, which is just sufficient so that the machine is operating at UPF, that means the machine is not delivering any reactive power. If the current is less than IF, the machine will start drawing reactive power because the corresponding load would be a capacitive load. If the rotor current is more than the field current IF, the power factor of the load will be lagging, means the generator would be delivering reactive power. A synchronous machine, it can operate at no load. Ideally speaking, there can be no real power transfer should happen, and it can still behave as an inductor or a capacitor depending on what is the reactive power control which is setting the corresponding field current. And there are special synchronous motors installed in power networks specifically for reactive power control perspective. We will also talk about this reactive power control perspective when we talk about transmission line models, where we will discuss at length about reactive power compensation. And synchronous motors behaving as synchronous condensers are one beautiful way of maintaining the reactive power or compensating reactive power in three-phase power networks. So synchronous motor not transferring or absorbing any real power. Ideally, no machine can have no real power transfer. It will definitely be consuming some real power, but that real power can be minimized as long as with proper good design. And synchronous motors can behave as inductors or capacitors, and we call those special motors to be synchronous condensers. Very useful for reactive power compensation. We'll conclude today's discussion with a simple example. We have a 3-phase 4 kV 400 kVA synchronous motor, a small motor, which is sort of installed with other induction motor loads in a given plant. Those motor loads, induction motor loads, are of 500 kVA operating at 0.8 power factor lagging, and the mechanical load on the synchronous motor is 300 kVA at unity power factor at 4 kV rated voltage. So 4 kV is the rated line-to-line voltage. What we have to find is the overall power factor of the entire factory, which consists of different induction motor loads as well as the synchronous motor, and what can be the maximum power factor of this particular factory without overloading the synchronous motor and without changing its real power absorption basically. So synchronous motor is basically absorbing real power, and we have to find that to what extent can the power factor of the entire factory be maximized or improved without overloading the motor and without changing the real power. And under that condition, we have to find the motor current, synchronous motor current, and its corresponding power factor. So if we have to find the power factor, basically we have to find the net real power and the net reactive power at all instances. If you look at the motor loads, induction motor loads, which are operating at 500 kVA 0.8 power factor lagging, then P is apparent power into cos theta, which is 0.8. So basically 400 kilowatt is the power which is absorbed by the induction motors. Since the power factor is lagging, which is true for induction machines, so these induction motors are also consuming 300 kVAR as reactive power. How do I get 300 kVAR? Cos theta, if it is 0.8, it would essentially mean sin theta is 0.6, which is what is multiplied with 500 kVA to get 300 kVAR. So induction motors, they are consuming 400 kilowatt real power, 300 kilovolt ampere reactive power. The synchronous motor is operating at 300 kVA unity power factor, which means the reactive power which is handled by the synchronous motor is perfectly zero. And if we now have to find the net real power, which is real power absorbed by all motors in the factory, this is going to be 400 for induction motors, 300 for synchronous motor, which is over here. So net real power is 700 kilowatt, and net reactive power at this instant is only 300 kilovolt ampere reactive. So in a way, the overall power factor of this factory load, which is basically cosine of theta, where tan theta, theta being the impedance angle, is nothing but Q net by P net. So what we do is we take tan inverse of Q net by P net. Q net is 300, P net is 700, and then take the cosine of it. That would give us 0.9191 as the lagging power factor, because the net reactive power is still being absorbed by all the motors in the given factory. Now if you have to find the maximum kVAR reactive power which the synchronous motor can generate without getting overloaded, remember the synchronous motor is rated at 400 kVA and its real power should not change. Its real power is basically 300 kilowatt, which it is already consuming. So if this is S and this is P, we can also find the corresponding reactive power which this machine can generate, which without getting overloaded. So that would essentially be root over of S square minus P square, which is what is mentioned here. So 264.575 kVAR can be generated by the synchronous motor. So in a way, earlier, if 300 kVAR was the reactive power absorbed by the induction motors, 264.575 kVAR can be locally managed by the synchronous generator motor, which is placed along with the induction motor. So essentially, the grid supply for reactive power is only 35.425 kVAR with real power remaining as it is. And since the reactive power consumption has now decreased, the corresponding power factor of factory tends to be improved. So basically the new power factor is almost close to 1 with 0.99 lagging. It is still lagging because this reactive power is still being withdrawn or drawn from the electrical supply by the factory. The corresponding armature current of synchronous motor in terms of its maximum apparent power and 4 kV as the rated voltage is nothing but 400 kVA, which is the rated apparent power. If we take the per phase power, it is divided by 3, and then if we have to find the corresponding phase voltage of the synchronous motor. Line to line voltage is 4 kV. So if we divide it by root 3, we would have the phase voltage. So phase power divided by the phase voltage is nothing but 400 by root 3 into 4. The unit kV, the kV units, they all get cancelled, and essentially we are left with 57.74 amperes as the armature current of synchronous motor. The power factor of the synchronous motor is basically 0.75 leading. How? The motor is still absorbing 300 kilowatt of power and it is operating at 400 kVA, and it is still able to generate 264.575 kilovolt ampere reactive as the reactive power. So cos theta, which is also real power by apparent power, where P is 300, apparent power is 400 because the machine is operating at its maximum capacity, not getting overloaded. So power factor number becomes 0.75. It is now leading because the machine is able to generate this much amount of reactive power. With this, we conclude today's discussion. In the next discussion, we'll take up another interesting topic of synchronous generators on economic dispatch, and we'll understand how these different generators are able to generate or share the real power while maintaining system economics. Remember, as engineers, we all tend to design our systems or behave usually keeping the economics into consideration. Each one of us wants to maximize profit and minimize operational cost. Same is also true for generators or the corresponding owners or operators who operate these plants. So with that, I thank you and conclude this today's discussion. Thank you so much.